The universe is more than just vast. It's a living, breathing enigma, stretching further and faster into the unknown with every passing second. Picture this: galaxies speeding away from one another like cosmic dancers caught in an endless waltz, the very fabric of space itself unraveling into infinity. This isn't science fiction, it's our reality. What if I told you that the stars we gaze at in the night sky aren't just distant, many of them no longer even exist as we see them? The universe is expanding, reshaping everything we thought we knew about existence, time, and space. In this video, we're diving into 25 mind-blowing facts about the expanding universe, facts that will not only challenge your understanding of the cosmos, but may even shift the way you see yourself within it. From the secrets of its fiery origins to the mysteries of its infinite future, prepare to embark on a journey through the greatest story ever told, the story of everything. Are you ready to explore the wonders of the cosmos? Let's begin. Now turning to our first astonishing fact, the universe is expanding faster than the speed of light. At first glance, this might sound impossible, as nothing can travel faster than light, right? Well, here's the twist: the universe isn't breaking any cosmic rules. Instead, it's the space between galaxies that's stretching, causing them to move apart at incredible speeds. This mind-blowing phenomenon was first hinted at by the brilliant astronomer Edwin Hubble. In the 1920s, he made a groundbreaking discovery known as redshift. Imagine it like this: when light from a galaxy travels to us, it shifts toward the red end of the spectrum if that galaxy is moving away. Hubble noticed that nearly all galaxies exhibit this redshift, proving that they're racing away from each other. But it gets even more fascinating. Thanks to an enigmatic force called dark energy, the expansion of space is accelerating. This means that galaxies aren't just drifting apart, they're speeding up their escape. The result: some galaxies are now moving away at velocities that make it impossible for their light to ever reach us. The universe, it turns out, is a master of surprises, redefining not only what's possible but what's even observable. Let's dive deeper into another cosmic revelation. Moving forward, let's unravel a common misconception about the Big Bang. Contrary to popular belief, it wasn't an explosion in the traditional sense, like a bomb going off in space. Instead, it was the rapid expansion of space itself. To put it simply, there wasn't an empty void waiting to be filled with cosmic debris. There was no outside to explode into. Everything, including space and time, began expanding from a singular point. Now, let's picture it with a simple analogy. Imagine a balloon covered in tiny dots. As you blow air into the balloon, the dots move farther apart from one another. This isn't because the dots themselves are flying off, but because the surface of the balloon, the space they exist on, is stretching. This is much like what happened during the Big Bang. Space didn't expand into anything. It created its own stage as it stretched. By understanding this, we can glimpse the extraordinary way the universe grew from a minuscule, unimaginably dense state to the sprawling cosmic expanse we see today. And yet, the story doesn't end here. Let's continue into the next chapter of this cosmic tale. Now turning to one of the most fascinating remnants of the Big Bang, let's explore the cosmic microwave background radiation. This faint, almost imperceptible glow is essentially the afterglow of the universe's fiery birth. Imagine it as the heat left over from an enormous fire that burned nearly 14 billion years ago. When scientists first detected this radiation in the 1960s, it was like uncovering a time capsule from the earliest moments in the universe's history. At the time of the Big Bang, the universe was unimaginably hot and dense. As it expanded, it cooled down, and eventually, around 380,000 years after the Big Bang, the first atoms formed, allowing light to travel freely through space for the first time. The light from that era has been stretched and cooled over billions of years as the universe expanded, and now we see it as microwave radiation. But what makes this so special? Well, this cosmic microwave background radiation acts like a baby picture of our universe, showing us what it looked like when it was just a few 100,000 years old. Tiny variations in this radiation reveal clues about the early distribution of matter and energy, helping us understand how galaxies and clusters of galaxies formed. In simple terms, it's like a cosmic map, preserving the universe's earliest secrets and confirming its fiery origin. Without this groundbreaking discovery, our understanding of the Big Bang and the universe's early years would be far less complete. And while this glow from the past is incredible, even more mind-boggling facts about our expanding universe await us. Let's delve further. Moving forward, let's unravel one of the most surprising truths about the universe: it has no center. It's a concept that defies our everyday understanding of space and movement. You might imagine the universe's expansion as a giant explosion from a single point, but that's not accurate. Instead, the expansion is happening evenly across space, meaning there's no specific middle from which everything is spreading out. Picture it like the surface of a balloon being blown up. As the balloon inflates, every point on its surface moves away from every other point, and no single spot on the balloon can be called the center of the expansion. Similarly, in our universe, every galaxy appears to be moving away from every other galaxy because space itself is stretching. This uniform expansion makes it seem, from any galaxy's perspective, as if it is at the center of the universe, but that's just an illusion created by the way space expands. This idea reshapes how we think about our place in the cosmos. The universe doesn't revolve around one point, and by extension, we aren't at the center of it either. This realization humbles us and broadens our perspective, emphasizing just how vast and interconnected the cosmos truly is. And as we continue to explore the wonders of the expanding universe, we uncover even more phenomena that challenge the limits of our imagination. Stay with us as we dive deeper. Now turning to another fascinating aspect of the expanding universe, let's delve into the movement of galaxies and what it reveals. Have you ever noticed how the sound of a passing car changes as it moves away from you, with the pitch dropping? This effect, known as the Doppler effect, doesn't just apply to sound, it happens with light too. When astronomers observe galaxies, they notice their light is shifted to the red end of the spectrum, a phenomenon aptly called redshift. This shift happens because these galaxies are moving away from us, and as they do, the light waves they emit get stretched out, making their color appear redder than it truly is. The farther away a galaxy is, the faster it appears to be speeding away, and the greater its redshift. This groundbreaking discovery, first made by Edwin Hubble, was one of the key pieces of evidence that confirmed the universe is expanding. It's as if the entire cosmos is stretching out like a massive rubber band. This stretching doesn't just give us a sense of movement, it also provides a way to measure the vast distances across space. By analyzing the redshift of a galaxy, scientists can calculate how far away it is and how fast it's moving. This understanding reinforces the idea that we live in a dynamic universe, one that's constantly changing and evolving. But this movement of galaxies is not random, it's a direct result of the cosmic expansion itself, a phenomenon that continues to redefine our view of the universe. And the more we uncover, the more we realize just how much there is left to discover in the ever-stretching tapestry of space. Stay tuned, as the next fact will take us even further into the mysteries of this incredible expansion. Moving forward, let's uncover a truly unsettling implication of the universe's relentless expansion. Imagine looking up at the night sky, filled with countless twinkling stars and galaxies. Now picture a future where some of those galaxies vanish, not because they cease to exist, but because they've moved so far away that their light can no longer reach us. This isn't science fiction, it's a real consequence of the universe's accelerating expansion driven by dark energy. As space stretches, the distance between us and these galaxies grows so immense that even light, traveling at its staggering speed, cannot bridge the gap. Over time, the light waves get stretched out so far that they shift beyond the visible spectrum into undetectable wavelengths, making these galaxies effectively invisible. This means that future astronomers may find themselves staring into a much emptier cosmos, unable to observe or study parts of the universe that we can see today. It's a sobering reminder that the universe we observe is not static, it's fleeting, and our current view of it is unique to this moment in cosmic history. This looming invisibility of galaxies doesn't just redefine our understanding of the universe's expansion. It also underscores the importance of studying the cosmos now, while we still have access to this breathtaking wealth of information. But as chilling as this prospect may seem, it's only one layer of the mysteries that come with living in an ever-expanding universe. Up next, we'll explore how much of the universe we can actually see, a small and humbling fraction of its true scale. Stay with us as we continue unraveling the awe-inspiring secrets of space. Now turning to another fascinating reality, let's consider the observable universe, what we can actually see versus the vast cosmic expanse that exists beyond our perception. The observable universe is like a window limited by two key factors, the speed of light and the age of the universe. Light, as fast as it is, takes time to travel. When we look at distant stars and galaxies, we are not seeing them as they are now, but as they were when their light first began its epic journey to reach us. The farther away an object is, the older the light we're observing. And here's the catch: because the universe is only about 13.8 billion years old, light from beyond a certain distance simply hasn't had enough time to reach us. This means our observable universe is essentially a cosmic bubble with a diameter of about 93 billion light-years, stretching as far as this ancient light allows. But make no mistake, this bubble is just a fraction of the universe's entirety. Beyond what we can see lies a potentially infinite expanse, filled with countless galaxies, stars, and unknown wonders. The unseen universe may be billions, trillions, or even infinitely larger than what we can ever observe, and we might never access it due to the limitations imposed by the speed of light and the relentless expansion of space. This humbling realization reminds us that what we know is just a sliver of the greater cosmic story, leaving us to wonder about the mysteries that lie beyond the reach of our telescopes and imaginations. Yet, even within our observable universe, there's so much to uncover, and our next journey will dive into the enigmatic force that drives this cosmic expansion itself. Stay tuned as we unravel the secrets of dark energy and its dominant role in shaping the fate of everything we know. Moving forward, let's unravel the mystery of dark energy, the enigmatic force responsible for the accelerated expansion of our universe. Imagine this: while gravity works to pull objects together, dark energy does the exact opposite, pushing galaxies apart with ever-increasing speed. It's almost as if space itself is stretching more and more as time goes on. Here's what's truly astonishing: dark energy isn't just a minor player in the universe. Scientists estimate that it makes up about 68% of everything that exists. That's right, the vast majority of the universe is this invisible, intangible force that we still barely understand. Unlike matter, which we can see, touch, or detect with instruments, dark energy doesn't emit light and doesn't interact with it in any way we currently know of. It was first discovered when astronomers noticed that distant galaxies are not just moving away but are accelerating their retreat. This observation turned our understanding of the cosmos upside down. Instead of gravity slowing down the expansion after the Big Bang, the universe is actually speeding up, defying what we once believed to be possible. What is dark energy exactly? That's the trillion-dollar question. Some theories suggest it might be a property of space itself, while others propose it's tied to a field or force beyond anything described by our current physics. Despite being a dominant part of our universe, dark energy remains one of the greatest mysteries in modern science. It's a reminder of how much we still have to learn about the cosmos and its intricate workings. But dark energy doesn't just shape the present, it holds clues about the universe's ultimate fate. Will the expansion continue forever, or will dark energy eventually lead to some dramatic end? For now, it seems every discovery about dark energy opens more questions than it answers, keeping scientists and all of us mesmerized by the unknown. And speaking of mysteries, our next focus will explore another piece of the cosmic puzzle, the universe's seemingly flat geometry. Now turning to the universe's destiny, let's dive into the fascinating possibility that it will expand forever. Current theories suggest that this endless expansion could lead to a scenario known as the Big Freeze. Imagine this: a future where the universe becomes so vast and stretched that stars run out of fuel, galaxies drift further apart, and new stars can no longer form. Over an unfathomable amount of time, even the smallest sources of warmth and energy could fade away, leaving the universe cold, dark, and lifeless. This is the ultimate fate predicted by the Big Freeze, where all activity grinds to a halt as the infinite expanse of space becomes eerily still. Why do scientists believe this could be our universe's destiny? The key lies in the mysterious force we just explored: dark energy. Its relentless push accelerates the universe's expansion, pulling galaxies farther apart at breakneck speeds. Unlike gravity, which could potentially slow or stop expansion, dark energy shows no signs of weakening over time. In fact, if it continues to dominate as it does now, it all but guarantees a cosmos that stretches endlessly into the future. Some theories even suggest that as expansion continues, matter itself could be pulled apart, though this idea, often called the Big Rip, is much more speculative. For now, the Big Freeze is considered the most likely outcome. It's a sobering thought: the very force that gave rise to our vibrant universe might one day turn it into a vast, icy void. But while this fate feels bleak, it also highlights how little we truly understand the forces shaping our existence. Scientists continue to study dark energy and expansion in hopes of uncovering more clues, knowing that every new discovery brings us closer to understanding the ultimate fate of the cosmos. And speaking of forces shaping the universe, let's now explore one of its more surprising characteristics: its intriguingly flat geometry. Now turning to its intriguingly flat nature, the geometry of the universe is one of the most surprising revelations in modern cosmology. When we think of something flat, we often imagine a piece of paper or a calm, smooth surface. But in the case of the universe, flatness refers to its overall shape and the way space behaves on a grand scale. Scientists have determined that the universe is flat, not curved like a sphere or saddle. Through meticulous observations of the cosmic microwave background radiation, the faint glow of energy left over from the Big Bang. This ancient light provides a blueprint of the early universe, encoding subtle clues about its shape. By analyzing the patterns and fluctuations in this radiation, astronomers found that light travels across the cosmos in straight lines, a hallmark of a flat geometry. If the universe were curved either inward or outward, these light paths would bend, creating noticeably different patterns. The implications of a flat universe are profound. It suggests that the total density of matter and energy in the cosmos is perfectly balanced, a delicate harmony where the forces shaping the universe neither cause it to collapse nor accelerate expansion in a runaway fashion beyond what we observe. This discovery aligns with the theory of cosmic inflation, which posits that an early period of rapid expansion smoothed out any irregularities, flattening the universe much like a balloon that inflates evenly. Yet the question remains: how and why did the universe end up with such remarkable precision? Unraveling this mystery could deepen our understanding of the cosmos' origins and destiny, offering insight into the extraordinary balance that underpins everything we see. And while this flat nature might seem ordinary at first glance, it's just another reminder of the hidden marvels that define the universe's structure. Moving forward, let's delve into how scientists calculated the universe's astonishing age, an achievement that unveils its long and complex history. Now turning to the astonishing calculation of the universe's age, scientists have determined that it is approximately 13.8 billion years old, an almost unimaginable timeline that stretches far beyond our everyday experience. This incredible discovery was made possible through the analysis of the cosmic microwave background radiation, the faint afterglow of the Big Bang that serves as a time capsule from the universe's infancy. By studying this ancient light, astronomers can pinpoint how long it has been traveling through space, giving us a direct measurement of the universe's age. Another key tool in this calculation is the Hubble constant, which represents the rate at which the universe is expanding. By observing the movement of galaxies and the redshift of light, astronomers can determine how quickly space has expanded over time, effectively rewinding this cosmic expansion to its very beginning. Combining these methods with advanced models of the early universe allows scientists to cross-check their findings with remarkable precision. This process not only reveals the universe's age, but also provides a framework for understanding its evolution, from the searing heat of the Big Bang to the sprawling cosmos we observe today. However, this calculation is not just a number, it connects us to a vast history, showing us how the cosmos grew, changed, and set the stage for everything we see around us. And as we marvel at the timeline of the universe, let's shift our focus to its uneven expansion, a phenomenon shaped by the intricate distribution of matter and energy across the cosmic tapestry. Moving forward, let's explore the fascinating phenomenon of the universe's uneven expansion. While space itself stretches outward, it doesn't do so uniformly. This irregularity is largely due to the way matter and energy are distributed throughout the cosmos. Imagine sprinkling sugar on a table. Some areas will end up with dense clumps while others remain sparse. Similarly, the universe is filled with dense regions such as galaxy clusters and vast, nearly empty areas known as cosmic voids. These differences lead to variations in how quickly different parts of the cosmos expand. In regions with a higher concentration of matter, gravity pulls more strongly, slowing the rate of expansion. On the other hand, in less dense areas, the push of dark energy dominates, causing space to expand more rapidly. Over billions of years, this uneven expansion has sculpted the universe into its current intricate structure, with vast networks of galaxies connected by filaments and separated by immense voids. This patchwork of faster and slower expansion reveals the delicate interplay between gravity, dark energy, and the distribution of matter. It's a reminder that the universe's growth is not a simple, uniform process, but a dynamic, complex ballet shaped by the forces at play within it. As we marvel at this cosmic choreography, let's delve into how dark matter, an invisible but critical component, influences this grand expansion. Now turning to the mysterious role of dark matter in the universe's expansion, we find ourselves uncovering one of the most perplexing puzzles of modern astrophysics. Dark matter is an unseen substance that neither emits nor absorbs light, making it completely invisible to even the most advanced telescopes. Yet, its presence is undeniable because of the immense gravitational influence it exerts. Imagine a hidden scaffolding, an invisible framework holding galaxies together. It's dark matter that provides this structure. While dark energy pushes the universe to expand at an accelerating rate, dark matter acts as a counterbalance in some scenarios, its gravitational pull resisting this outward push. In regions where dark matter is more concentrated, such as around galaxy clusters, this invisible force helps slow down the pace of expansion, creating pockets where the pull of gravity momentarily dominates over the expansive push of dark energy. Without dark matter, galaxies might not have enough gravity to stay intact, and the cosmic web of structures we see today would simply not exist. This interplay between dark matter and dark energy is like a cosmic tug of war, shaping the universe's behavior in ways we are only beginning to understand. With its mysterious influence quietly at work, dark matter continues to play a pivotal role in the grand evolution of the cosmos. As we pull back the curtain even further, let's unravel the paradoxical reality of galaxies colliding amidst an ever-expanding universe. As the next chapter of our cosmic exploration begins, we dive into the fascinating paradox of galaxies colliding despite the relentless expansion of the universe. At first glance, it seems contradictory. How can galaxies move toward each other and collide when the universe is stretching in all directions? The answer lies in the powerful force of gravity. While the expansion of space causes most galaxies to drift apart, gravity works much closer to home. Galaxies that are part of the same cosmic neighborhood, such as those within galaxy clusters, are bound together by their mutual gravitational pull. This force can be so strong that it overcomes the outward push of the universe's expansion. Take our galaxy, the Milky Way, and its neighbor, the Andromeda Galaxy, for example. Despite being separated by an immense distance of over 2 million light-years, their gravitational pull on each other is so great that they are destined to collide in about 4.5 billion years. When galaxies merge, they don't crash together like solid objects. Instead, their stars and planetary systems weave through each other because of the vast spaces between them. However, the immense gravitational forces during these events can dramatically reshape both galaxies, triggering bursts of star formation and creating entirely new cosmic structures. These galactic collisions, rather than being destructive, often lead to spectacular transformations, illustrating how gravity acts as a sculptor in the ever-changing universe. And so, even in a cosmos dominated by expansion, the dance of colliding galaxies reminds us of gravity's incredible power to defy the odds. Moving forward, let's explore the curious reality of why this very expansion is slower in our own local group of galaxies. Now turning to the curious case of our own cosmic neighborhood, let's explore why the expansion of the universe seems to take a backseat in the local group of galaxies. While the universe as a whole is stretching out, here in our local group home to the Milky Way, the Andromeda Galaxy, and dozens of smaller galaxies, gravity holds the reins. The mutual gravitational pull between these galaxies is so strong that it effectively counteracts the outward push of the cosmic expansion. Imagine a group of friends holding hands tightly while standing on a rubber sheet being stretched. No matter how much the sheet expands, their grip keeps them together. A similar scenario plays out in the local group. The distances between these galaxies remain relatively stable because their gravitational bond is far stronger than the influence of the universe's overall expansion. This gravitational stability is why, instead of drifting apart, some galaxies within the group are slowly moving toward one another, with the Milky Way and Andromeda marking an eventual cosmic rendezvous. This phenomenon highlights a fascinating exception to the universal rule of expansion, reminding us that the forces shaping the cosmos can play out differently depending on scale. And with that thought, let's shift our attention to an even more incredible concept: the rapid inflation of the universe that occurred in its earliest moments, far surpassing the speed of light. Now turning to the astonishing phenomenon of cosmic inflation, let's dive into the incredible moment that redefined everything we know about our universe's birth. Shortly after the Big Bang, the universe underwent an unimaginably brief period of rapid expansion called inflation. In less than a fraction of a second, the universe grew from a size smaller than an atom to something roughly the size of a grapefruit, an expansion so extreme that it outpaced the speed of light. But before you wonder if this breaks any cosmic rules, it's important to note that nothing within the universe traveled faster than light. Rather, it was space itself that expanded, carrying everything within it along for the ride. Picture a balloon being inflated at lightning speed, with every point on its surface zooming away from every other point faster than you can blink. This mind-boggling event laid the groundwork for the universe as we see it today, smoothing out irregularities and creating the nearly uniform structure we observe in the cosmic microwave background radiation. Without inflation, the universe would likely be a chaotic and uneven mess. Instead, this brief but powerful phase set the stage for galaxies, stars, and planets to form billions of years later. Inflation is not just an intriguing concept, it's a key piece of the puzzle in understanding our cosmic origins. And with that, let's unravel yet another mystery, the ongoing debate surrounding how we measure the rate of the universe's expansion. Now turning to the fascinating debate over the Hubble constant, let's explore why this seemingly straightforward measurement has become one of the most puzzling mysteries in modern cosmology. The Hubble constant represents the rate at which the universe is expanding, and it is central to understanding its size, age, and ultimate fate. However, what should have been a consistent value is causing confusion because two primary methods of measuring it are giving different results. The first method, which involves observing nearby objects like Cepheid variable stars and supernova to calculate distances and their redshifts, yields one value for the Hubble constant. Meanwhile, the second method uses observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, and provides a slightly different result. The discrepancy between these two methods is small but persistent, and it has left scientists scratching their heads. Could it be due to unseen forces in the universe that we have yet to understand, or perhaps subtle errors in our measurements? Some even speculate that the answer may point to entirely new physics beyond our current theories. This ongoing disagreement has sparked intense research and debate, with astronomers around the world striving to reconcile the differences. It's a reminder that while we've made incredible progress in unraveling the secrets of the cosmos, some of its deepest mysteries still elude us. And speaking of deep mysteries, let's explore how looking at distant galaxies allows us to see into the universe's very past. Moving forward, let's dive into the incredible concept of how observing distant galaxies is like peering back in time. Light, the fastest thing in the universe, still takes millions or even billions of years to travel across the vast cosmic distances separating us from these faraway galaxies. This means that when we look at a galaxy that is a billion light-years away, we aren't seeing it as it is today, but rather as it was a billion years ago. It's like having a time machine built into the fabric of the universe itself. The further away a galaxy is, the older the light we're seeing, allowing us to witness events that unfolded when the universe was much younger. For example, some of the most distant galaxies ever observed appear as tiny, dim specks of light, but they are actually snapshots of the first galaxies forming shortly after the Big Bang. This fascinating phenomenon not only helps us understand the early stages of galaxy formation, but also lets us piece together an unbroken timeline of the universe's evolution. As we continue to build more advanced telescopes like the James Webb Space Telescope, we're pushing this cosmic time machine further than ever before, uncovering sights that were once thought to be beyond our reach. But what does this mean for our understanding of light itself and how it behaves across such vast stretches of space? That's where the concept of light stretching, or redshift, becomes the next piece of this cosmic puzzle. Now turning to the intriguing behavior of light across the vast expanses of the universe, let's explore how the expansion of space itself stretches light waves. This phenomenon, known as redshift, occurs because as space expands, it pulls the wavelengths of light traveling through it, making them longer. Longer wavelengths correspond to the redder part of the light spectrum, hence the name redshift. Imagine it like this: if you were holding a rubber band and then stretched it, the band would elongate. Similarly, light that travels through the ever-expanding fabric of the universe gets stretched along the way. But this isn't just about color. Redshift is a powerful tool that lets astronomers measure how fast objects like galaxies are moving away from us, and crucially, how far they are. The greater the redshift, the further away and faster a galaxy is receding. This is a direct observation of the universe's accelerating expansion, a discovery that revolutionized our understanding of cosmology. Redshift also allows scientists to look back in time and map out the history of the cosmos. By analyzing the light from ancient galaxies, astronomers can determine not only their distance but also what the universe was like when that light began its journey billions of years ago. It's a testament to how interconnected light and space are, each helping us unlock the secrets of the universe's past, present, and future. And speaking of light's journey through space, it's fascinating to think about how these tiny particles of light called photons carry the story of the cosmos across unimaginable distances. But what happens when the very structure of the universe influences how we measure its growth and expansion? That's the next exciting question to unravel. Moving forward, let's dive into the incredible moment that marks the universe's dense and fiery beginning. In its earliest stages, the universe was unimaginably compact, with all its matter and energy squeezed into an incredibly small, dense, and hot state. This idea forms the foundation of what we call the Big Bang theory. Rather than being an explosion in space, this was an expansion of space itself, where the universe began to stretch and cool, giving rise to the cosmos we observe today. Two key pieces of evidence confirm this dense beginning. First is the cosmic microwave background radiation, a faint glow that fills the universe and is often referred to as the afterglow of the Big Bang. This ancient light acts as a snapshot of the universe when it was just 380,000 years old, revealing its early structure and composition. The second piece of evidence comes from what scientists call Big Bang nucleosynthesis, the process that occurred in the first few minutes of the universe's existence. During this brief but critical period, the extreme temperatures and densities allowed the formation of the lightest elements, such as hydrogen and helium, which still make up the vast majority of the universe's matter today. These elements and their observed abundances perfectly align with predictions made by the Big Bang model, strengthening our understanding of the universe's hot and dense origins. It's awe-inspiring to think that everything we see today, planets, stars, galaxies, and even life itself, emerged from such a searing and compact state. But what's equally fascinating is how this dense beginning set the stage for the complex structures we observe across the cosmos. Let's now explore what happens as this early universe expands and takes shape, carving out the vast cosmic landscape we find ourselves in today. Now turning to the fascinating aftermath of the universe's relentless expansion, let's explore how it has sculpted the cosmic landscape into a tapestry of extremes. As space continues to stretch, galaxies are not evenly distributed but instead gather together into massive clusters and superclusters, bound by their mutual gravitational pull. These cosmic gatherings are like islands of matter in an ocean of nothingness. Between these clusters lie vast, almost incomprehensibly empty regions known as cosmic voids. These voids span hundreds of millions of light years and contain hardly any galaxies, stars, or other visible matter. But why do these voids exist? It all comes down to the interplay of gravity and expansion. In the early universe, tiny variations in the density of matter were amplified by gravity over billions of years. Areas with slightly more matter attracted even more, pulling material together to form galaxies and clusters, while less dense regions were left behind to grow emptier over time. Today, these voids are some of the largest structures in the universe, yet they remain eerily vacant. Interestingly, these empty expanses are not completely without significance. They provide critical clues to the processes that shape the cosmos, acting as natural laboratories for studying dark energy and the mysterious forces driving the universe's accelerated expansion. What's even more intriguing is how these voids highlight the incredible contrast in the universe's structure. On one hand, dense, bustling regions teeming with stars and galaxies, and on the other, serene, silent voids stretching across unimaginable distances. This remarkable diversity is a testament to the universe's dynamic and evolving nature. So, as we delve deeper into the mysteries of cosmic structure, let's consider the forces at play that have created these awe-inspiring contrasts and how they continue to shape the universe we inhabit. Moving forward, let's unravel the intriguing story of how the rate of cosmic expansion has evolved over the lifetime of the universe. Right after the Big Bang, the universe underwent an astonishing event known as cosmic inflation. During this fleeting fraction of a second, the universe expanded exponentially faster than the speed of light itself. This extraordinary burst of growth smoothed out the fabric of space, setting the stage for the cosmos we observe today. However, once inflation ended, expansion slowed dramatically as gravity took hold. For billions of years, the combined gravitational pull of matter, including dark matter, worked to decelerate the universe's growth. It seemed as though expansion might gradually come to a halt, but then something unexpected happened. Roughly 5 billion years ago, the influence of dark energy began to dominate. Dark energy, this mysterious and unseen force, acts in direct opposition to gravity, pushing galaxies apart. As a result, the universe's rate of expansion began to accelerate once more and continues to do so today. This means that the space between galaxies is not only growing but doing so at an ever-increasing pace. What's especially fascinating is that this changing rate of expansion reveals a great deal about the interplay between forces in the universe, how gravity reigned supreme in the early epochs, but was eventually overtaken by dark energy as the cosmos aged. Each of these phases has left an indelible mark on the structure and dynamics of the universe. Understanding this evolution helps us not only grasp the cosmic past, but also predict what might lie ahead. Will dark energy continue to accelerate expansion forever, or could new forces emerge to alter the universe's path? These are the profound questions that drive modern cosmology, leading us ever deeper into the mysteries of the expanding universe. Now turning to the fascinating interplay between cosmic expansion and time, let's explore how the expanding universe challenges our very understanding of space-time. At its core, the concept of time is deeply intertwined with space itself, as described by the theory of general relativity. In this framework, massive objects warp the fabric of space-time, creating what we perceive as gravity. But as the universe expands, the very structure of space-time changes, stretching across vast cosmic distances. This stretching has profound implications for how we experience and measure time. Imagine light traveling from a distant galaxy. Because the space through which the light travels is expanding, the light waves themselves are stretched, a phenomenon we call redshift. This means that as we look farther into the universe, we are not just seeing distant objects but also looking back in time. Galaxies billions of light years away appear as they were billions of years ago, frozen in a cosmic time capsule, giving us a glimpse into the universe's ancient history. But it gets even stranger. The accelerating expansion caused by dark energy means that the very fabric of time is being warped in unprecedented ways. As regions of the universe move farther apart, the concept of simultaneity, what it means for two events to happen at the same time, becomes fuzzier on a cosmic scale. In effect, time flows differently depending on your location in the universe and the relative motion of objects around you. This challenges our intuitive understanding of time as a steady, universal progression. Even more mind-bending is the notion that, in an ever-expanding universe, some regions may eventually become entirely unreachable, their light never able to reach us due to the relentless acceleration of space. In such scenarios, the timeline of the observable universe would be forever altered, with distant events forever locked away from our view. All of this reveals that time is not a fixed background but a dynamic entity shaped by the forces governing the cosmos. Understanding this intricate relationship between time and expansion not only deepens our insight into the universe but also invites us to reconsider the very nature of reality itself. Now turning to one of the most profound mysteries of cosmology, let's explore the theories surrounding the ultimate fate of the universe. Despite all we have uncovered about the cosmos, its final destiny remains shrouded in uncertainty, offering a range of fascinating possibilities. One such theory is called the Big Rip. In this scenario, dark energy, the mysterious force accelerating the universe's expansion, continues to grow stronger over time. If this happens, it could eventually overpower all other forces, tearing apart galaxies, stars, planets, and even the very atoms that make up matter itself. Imagine a future where the universe becomes an endless sea of individual particles, separated by unbridgeable distances. Another possibility is the opposite extreme, known as the Big Crunch. This theory suggests that the expansion of the universe might someday reverse if the gravitational pull of matter, both visible and dark, becomes strong enough to overcome the push of dark energy. In this case, the universe would stop expanding and gradually collapse in on itself, shrinking until it reaches an unimaginably dense and hot state. This could potentially set the stage for a new Big Bang, restarting the cycle of cosmic creation. A third and equally intriguing idea is the heat death or the Big Freeze. In this scenario, the expansion of the universe continues indefinitely, but at a steady pace. Over time, stars burn out, galaxies drift apart, and the universe grows colder and darker. Eventually, all energy would be evenly distributed, leaving behind a vast, frozen expanse where no processes can occur, effectively ending all activity in the cosmos. The fate of the universe hinges on the enigmatic nature of dark energy and the precise balance of matter and energy throughout space. As scientists study these forces, they inch closer to unlocking the secrets of our cosmic destiny. While we may not yet have the answers, contemplating these possible endings reminds us of the staggering scale and complexity of the universe and the persistent drive of humanity to understand it, no matter how vast the unknown may be. Now turning to our final fascinating fact, let's delve into how the expanding universe acts as a cosmic key, unlocking the secrets of its origins, composition, and ultimate fate. By studying the patterns and pace of expansion, scientists have pieced together a story that begins over 13 billion years ago with the Big Bang, when the universe burst into existence from an incredibly hot, dense state. The discovery of the cosmic microwave background radiation, a faint afterglow of that primordial state, has provided vital clues about the universe's infancy, confirming that space itself has been stretching ever since. Observing the movement of galaxies has revealed the presence of dark energy, the enigmatic force driving accelerated expansion, and dark matter, an invisible yet massive component that sculpts the cosmic web. These discoveries not only reshape our understanding of what the universe is made of, but also allow us to predict its potential destinies, as we explored with theories like the Big Rip, the Big Crunch, and the heat death. Every photon stretched by expanding space and every redshifted galaxy tells us a part of a grander story, one that spans time, space, and the very essence of existence. The quest to understand expansion underscores the brilliance of human curiosity and our relentless desire to answer the most profound questions about where we came from, what we are, and where we are headed. Though we may only see a fraction of the universe and grasp just a sliver of its mysteries, the knowledge we gather brings us ever closer to understanding the cosmos, not as mere observers, but as active participants in its unfolding story. With this, we conclude our journey through these astounding facts, a journey that reminds us of the boundless wonders that lie in the great expanse above. If you found these discoveries as awe-inspiring as we did, be sure to like this video, share it with fellow space enthusiasts, and subscribe for more deep dives into the mysteries of the universe. Let us know your favorite fact in the comments below, and until next time, keep looking up and marveling at the cosmos. Now turning to the fascinating implications of faster-than-light expansion, let's clarify a common misconception. This phenomenon doesn't mean objects in the universe are physically traveling through space faster than light itself. Instead, it's space itself that is expanding, carrying galaxies apart with it. This crucial distinction aligns perfectly with the principles of general relativity, which govern the behavior of space and time. Unlike the speed of light, which applies to objects moving within space, there's no universal speed limit for the expansion of the fabric of space itself. This is why galaxies beyond a certain distance appear to recede from us faster than light, not because they're breaking any cosmic rules, but because the vast canvas of space is stretching at that incredible rate. And here's where it gets mind-blowing. This expansion isn't just pushing galaxies apart, it's redefining the very concept of distance and boundaries in the universe. Take the observable universe, for instance. The edge of what we can see is not a static boundary. Every moment, as space expands, galaxies that were once invisible due to their immense distance are brought into view, while others slip beyond our observational reach as their light is stretched into wavelengths too faint to detect. This dynamic edge challenges our understanding of what it means to map the universe. It's like trying to navigate an ever-expanding balloon where the surface keeps growing and what lies beyond remains a tantalizing mystery. The faster-than-light expansion also hints at a universe that could be far, far larger than anything we could ever see or measure. If the observable universe is just a fraction of the whole, what unimaginable wonders might exist beyond our cosmic horizon? From this perspective, the implications of faster-than-light expansion stretch our minds as much as space itself stretches light, inviting us to ponder not only the size of the universe but also the profound nature of reality itself. Moving forward, let's delve into one of the most perplexing and transformative forces in our universe, dark energy. To begin with, dark energy is not something we can see, touch, or even directly measure. Instead, its existence is inferred from the baffling observation that the universe's expansion is not slowing down, as one might expect due to gravity, but is instead accelerating. This startling discovery was first confirmed in the late 1990s when scientists observed distant supernovae, dying stars, appearing dimmer than anticipated. This dimness suggested they were farther away than their redshift implied, leading to the realization that something unknown was driving the universe apart at an ever-increasing rate. That something came to be known as dark energy, but what exactly is it? Well, that's the billion-dollar question. One leading theory suggests that dark energy could be an inherent property of space itself, referred to as the cosmological constant. Introduced by Albert Einstein over 100 years ago and later dismissed as his greatest blunder, this concept proposes that space has an intrinsic energy that doesn't dilute as the universe expands. In other words, as new space is created, more dark energy comes into play, fueling even faster expansion. Another hypothesis posits that dark energy might not be a constant at all, but a dynamic field that changes over time, often termed quintessence. If this were true, then dark energy could have behaved differently in the past and might even evolve in ways that could profoundly reshape the universe's future. There's also the possibility that our understanding of gravity itself is incomplete. Some scientists speculate that dark energy could be a sign that the laws of gravity, as we currently know them, need to be revised on cosmic scales. Imagine if our entire framework for understanding the universe had a hidden flaw waiting to be uncovered. Dark energy might just be the key to that revelation. What's even more astounding is how dominant dark energy is in the universe. It accounts for roughly 68% of the total cosmic makeup, vastly outweighing normal matter, the stuff we're made of, and even the mysterious dark matter. This means our entire existence as humans, as stars, even as galaxies, is dwarfed by the influence of this enigmatic force. Exploring dark energy is not just about understanding why the universe is accelerating. It's about confronting the limits of human knowledge and pushing the boundaries of physics itself. Could unlocking the mystery of dark energy lead to a new era in science that redefines everything we think we know? While the answers remain elusive, one thing is certain. Dark energy is a cosmic puzzle that challenges us to think bigger, reach further, and imagine the unimaginable. Now turning to the intriguing interplay of forces within our universe, let's explore the role of gravitational pulls in galaxy collisions. At first glance, it might seem contradictory. How can galaxies collide and merge when the universe is expanding, pushing them apart? The answer lies in the delicate yet overpowering force of gravity. While cosmic expansion drives galaxies away from each other on large scales, the gravitational pull between galaxies within close proximity often overpowers this outward push. When two galaxies come close enough, their mutual gravitational attraction pulls them together in a slow, cosmic dance that can last millions or even billions of years. Picture two ice skaters gliding toward each other. Drawn together by an invisible tether, they twirl around one another, sometimes merging into a unified, larger figure. In the case of galaxies, this dance of gravity results in spectacular collisions and mergers, reshaping the galaxy's structures and sparking bursts of star formation as gas clouds collide and compress. One of the most famous examples of such a collision is happening right in our cosmic neighborhood. The Andromeda Galaxy, our Milky Way's closest galactic neighbor, is on a collision course with us. In roughly 4.5 billion years, these two mighty galaxies will merge, creating a brand new, larger galaxy, likely an elliptical system, in an event that will be awe-inspiring but harmless to individual stars, as the distances between them are vast. These galactic mergers are not rare cosmic accidents, but rather essential events in the life cycle of the universe, shaping galaxies and redistributing matter and energy. They also serve as a reminder that while expansion governs the broader universe, gravity retains its dominance on smaller, local scales. Understanding this paradox of simultaneous expansion and local contraction helps us grasp the intricate balance of forces that define our cosmos. It demonstrates how the universe operates not as a collection of isolated phenomena, but as an interconnected, dynamic system, where even apparent contradictions, like galaxy collisions amid expansion, are part of a grand and harmonious design. Moving forward, let's unravel the mind-bending concept of time dilation in an expanding universe, a phenomenon that challenges our very perception of time itself. At its core, time dilation refers to the way time appears to move at different rates based on factors like relative motion and gravitational fields. Now, throw the expansion of the universe into the mix, and you get an even more fascinating twist on the nature of time. The expansion stretches not only space but also the fabric of time, meaning that as the universe grows, light traveling across vast distances undergoes changes that reveal time's elasticity. Here's an astonishing example. When we observe light from distant galaxies, we are not just peering across space but also back in time, seeing those galaxies as they were billions of years ago. Due to this expansion, the light waves are stretched or redshifted, which not only changes their color but also reflects the slowing down of events in those distant realms as seen from our perspective. In other words, time for faraway cosmic objects appears to move more slowly because of the immense distances and the accelerating expansion of space between us. To make this even more relatable, think of a documentary played in slow motion. The events happen in real time for the participants, but to the viewer, they appear slowed down and stretched out. In the cosmic sense, we are the viewers, watching the universe's distant past unfold in a kind of time lapse, slowed by the interplay of relativity and expansion. This effect becomes even more pronounced near incredibly massive objects like black holes, where gravity itself warps time, creating further layers of time dilation. Combining these effects with the universe's expansion gives a glimpse into the profound interconnectedness of space, time, and gravity. It's a humbling reminder that the experience of time is not universal but rather shaped by the circumstances of where and when you find yourself in the cosmos. This interplay between time dilation and expansion challenges us to rethink not just where we are in the universe, but when we are, offering a profound perspective on how the forces shaping the cosmos also shape our understanding of existence itself. Now turning to the fascinating yet unsettling concept of the Big Rip, let's explore what this theory could mean for the ultimate fate of the universe. At its core, the Big Rip hypothesizes that dark energy, the mysterious force driving the acceleration of cosmic expansion, could one day grow so powerful that it overcomes every other force holding the universe together. Imagine this: galaxies that are currently bound by gravity would eventually be pulled apart as dark energy continues to stretch space at an ever-increasing rate. But it wouldn't stop there. Over time, this relentless force could overpower the gravity holding stars together, tearing them apart. As expansion accelerates further, even atoms, the very building blocks of matter, could be ripped apart, leading to the complete disintegration of all structure in the universe. To put this into perspective, picture a rubber band being stretched to its limit. At first, it holds together even as the tension increases, but eventually the tension becomes too much and the band snaps. The Big Rip suggests that the universe could face a similar fate, with its fabric stretched to such extremes that it literally tears apart. What's truly mind-boggling is that this hypothetical future depends on the exact nature of dark energy, a phenomenon we still barely understand. If the strength of dark energy continues to grow over time, the Big Rip becomes more likely. On the other hand, if its influence stabilizes or weakens, other scenarios such as the Big Freeze or Big Crunch could unfold instead. The timeline for a potential Big Rip is also highly speculative, with estimates ranging from tens of billions to trillions of years in the future. This means it's not an imminent concern, but the idea challenges us to think about the long-term destiny of the cosmos. Whether or not the Big Rip becomes reality, the theory underscores just how much we have yet to learn about the forces shaping our universe. The very idea that the same energy driving the universe's growth could also spell its ultimate undoing is a profound reminder of the delicate balance that governs cosmic evolution. As we reach the conclusion, it's incredible to reflect on these 25 astounding facts about the expanding universe, a realm so vast, mysterious, and complex that it continues to challenge our understanding of reality itself. From the mind-bending discovery that the universe is expanding faster than light to the haunting possibility of the Big Rip, each of these revelations reminds us of just how extraordinary the cosmos truly is. The universe's expansion not only shapes the world we see, but also holds the key to unlocking its deepest secrets, its origins, its makeup, and perhaps even its ultimate fate. Whether it's the enigmatic force of dark energy, the fascinating role of dark matter, or the sheer enormity of time and space, every fact draws us deeper into the wonder and complexity of the universe. These mysteries inspire us to ask bigger questions and continue exploring the unknown. So as this journey through the cosmos comes to an end, let's keep our curiosity alive and our imaginations open. Share your favorite fact from this exploration in the comments below, and let us know which cosmic mysteries you'd like to learn about next. Be sure to hit that subscribe button, like this video, and turn on notifications so you'll never miss another journey into the wonders of the universe. Thank you for watching, and until next time, keep looking up.